Alright, so back where we're on atoms, we got talking about the nucleus. The nucleus has protons, which here have a positive charge. We did oxygen here, so we had 8 protons, and we have 8 neutrons. Neutrons are neutral, but they help hold the protons together so they don't repel each other into oblivion. Alright, and then attracted to the positive charge of the protons are the electrons, which are negative. But just like the moon is attracted by the gravitational pull between it and the Earth, but its speed is too great for it to be sucked into the Earth. Same thing here. The electrons are going so fast that they overcome the electrical pull between the positive and negatives that are attracted to each other. And so it's going fast enough that it stays in an orbit. And so very often these paths are called orbitals because they are orbiting around. Now, but they also found that they aren't just random orbits. They're like different levels. If an electron gets more energy, then it could scoot up to the next level. And so sometimes these are called energy levels, because the more energy that it has, faster it's going, the farther away from the nucleus it can get. Okay, but they don't just kind of get a little farther away, they jump into this next level. That gets into quantums, and we're not going to get into that, but there's definitely distinct levels that they jump up to. They don't just get a little farther and a little farther. They actually are on this level or the next level. And it turns out that this first energy level can hold 2 electrons, and then it's full, and that pushes any more electrons to the next level. Now this one would have a total of 8 altogether, because this is oxygen. And it would be neutral at this point, because it would have 2 and 6 makes a total of 8 negative charges. You have 8 positive charges, so it would be a nice neutral atom. But the second level can hold up to 8, and then oxygen doesn't have that many. And then it would have to go to the next one, and the next one would go to 8. Okay, although it can eventually hold up to 18. I think it's a little complicated. And then second, third, then it goes to 18, then it goes to 32. Okay, we're not going to worry about that a whole lot. Mostly we're worried about the outside layer is only going to have 8 at any given time, and that's what we're going to worry about. Now, these are also called, sometimes they're just called electron sort of orbitals or stuff. They're just called electron clouds, because basically these electrons are not just circling it, they're going in, besides circling it, they're also coming out toward us and back around, and they're going in all directions. So really they're just like a fuzzy blur around the atom where these electrons might be at any given moment. And so that blur is called the electron cloud. Okay, and the electron cloud is just where that electron is going so fast it would just be like a fuzzy ball looking thing almost, because it would be such a blur as it's whipping around there. Okay, and so that would be the electron cloud. Now, there can be as many as 7 of these electron orbitals or shells. Okay, as you get up to the bigger atoms. Okay, and like I said, the first one holds 2, the second and third one hold 8. The fourth and fifth one, if you got to that, would have a total of 18, and the 6th and 7th final ones would have a total of up to 32 on each level. Now, there are some of the very most recent one. 118 has got a complete 7th shell. If they were to make any artificial elements, would it go to another shell or another level or another orbital, however you want to call that? Don't know. We'll see. Okay, but anyhow, now of the electrons, these atoms, if they are neutral, for example, go back to our oxygen atom here. I'm going to get rid of those E's. I'm not going to draw them from now on, but just to show you that they're there and they are electrons. Okay. This is our electron. We have 8 positive charges, or 8 positive protons. We have 1, 2, 3, 4, 5, 6, 7, 8 negative electrons. So this would be a neutral atom. Now, if all atoms are neutral, they would never combine with anything, and that would not be good, because to make things, all the things on Earth that are made out of things, you have to combine these different atoms together with other atoms, and to do that you need a positive or a negative charge that they'll stick together to each other. Okay, and so what can happen is it can either lose electrons. If, to say this one lost 2 electrons, okay, now there's only 6. So you have 8 positives and 6 negatives, then it would have a +2 charge. Okay, now just for the record, for what it would usually, if it gained 2 more, which is what it would normally do, you would now have 10 electrons. So you got 10 negative charges, 8 positive charges, and this oxygen atom would have a -2 charge. Okay, and so that's okay, because that's basically how it would get a charge. So they can either gain or lose electrons. Now the only electrons they can gain or lose are the ones on their outside layer, whatever that is. It could be the 7th layer if you were a large atom. It could be the 6th layer if you're a little smaller one. It could be the 1st or 2nd layer if you're a very small atom. Okay, but the only electrons that can be gained or lost are on the outside layer, and these we called, in electricity we call them, in heat, and so we call them conduction electrons, but now we call them valence electrons, usually when we're talking about chemistry. The valence, sorry, that should have been an E, and I changed it back. Okay, valence. The valence electrons are the outside layer, and these are the ones that where you can either gain to fill it up, or you can lose them to get rid of it. Okay, and they will usually either try to fill up this outside layer or try to get rid of this outside layer. And so this is the valence. Comes from the same word as valiant, which means strong, because to get it strong or a charge, they have to gain or lose electrons off this level. So that's the valence electrons. All right, now to talk about atoms very much, you have to talk about the periodic table. The periodic table is basically a chart, and it panics some people when they say it, like, but actually it's a cheat sheet, if you will, with a lot of important information about atoms all put in one place, which makes it very easy for us to see it and understand it and find it when we need to look it up. Okay, now it also shows a lot of relationships between elements. If you understand why they are where they are, then you will learn a lot more about the elements. Okay, now in general there are about 90 to 92 elements that occur in nature and are found in nature. There have been found up to 118. Most of those above number 90 or 92, which is actually uranium, are only exist for a short time, and mostly have been forced together in laboratory conditions. Some of them only stay together for several nanoseconds before they fall back apart. Okay, so really, for all practical purposes, everything in the world is made out of 90 different ingredients. Okay, 92 ingredients, something to that effect. All right. Now, in order to find them in nature, they tend to be most of them. You don't find pure elements very often. Most of the time, they have combined with other elements. There are some exceptions. For example, gases in the air like oxygen and nitrogen are found as pure oxygen and pure nitrogen. Helium and some of the we'll call the noble gases, helium, neon, argon, krypton, and xenon, and radon, and so forth, are found. They're gases. Once again, they do not want to react with anything, so they're found pure. But most elements, it's fairly rare to find a pure element in nature because they tend to want to react with other things and form new things. Just think if everything in the world was just 90 different things, that's not very many things. So they have to be able to combine in lots of combinations to make all the different substances that there are in the world. All right. Now on the periodic table, if you look at one, it should technically look like this bottom one down here. Okay. And this is what it should look like. But in most of the time, it looks like this or like this with the letters in it. And what they've done is they've chopped off these two rows right here, shoved them together, and then put them underneath it. This is really just for convenience sake, so we can put it on a sheet of notebook paper in a reasonable length, so that you can still make it big enough that you can read all the parts. If you had to make it long and skinny like this bottom one, then the information would be so small that particularly us old people would have a hard time reading it. So we usually chop those two rows out. But just keep in mind that they actually belong right here, and that's what the periodic table should look like if it were complete. All right. Now, first thing you notice, there are symbols, two-letter symbols, and these are the symbols for the different elements. Okay. A lot of the names are pretty obvious. So you have hydrogen, which is an H. You have He for helium, F for fluorine, O for oxygen, N for nitrogen, C for carbon, B for boron. Those all pretty much make sense. Sometimes they're two letters like aluminum or Si for silicon, but those Once again, makes sense, usually just the first two letters. But then you have some that are just really odd, like for example, iron is Fe, silver is Ag, gold is Au, lead is Pb. Where did those names come from? And it usually goes back to the Latin names. The word for golden is aurum, A-U-R-U-M, and the first two letters of that is A-U. So those are the letters for gold. Plum, or plumbing, originally Romans made their pipes out of lead. So Pb, lead, stands for plumos, which was a word for plumbing. All right. Argentum was the name for silver, so the A and the G from that made silver. Argentina was named for this because of silver deposits there. Okay, and so the symbols are usually either Latin names or the first letter or a couple letters of their English name. All right. Now on the periodic table, you have basically vertical groups, these up and down groups like this. All right, and those are called either groups, or sometimes we'll say families. And generally speaking, elements that are in the same group have similar properties. For example, these are all +1, these all have a +2 charge, and so on. And so they have similar properties. They are similar type of materials and so forth. And that's why it's called a periodic table, because as they started listing them, they noticed that certain columns started repeating the same qualities. And a period is something that repeats over and over on a certain time scale or a certain order. And so since they repeat and have similar properties every so often, that's why it's called a periodic table. Up until then, they were just kind of making a list of them and so forth. But they started trying to organize them. Mendeleev was a very famous Russian scientist who eventually kind of got the basic table set up as we have it today. The periods then are the rows across. So the horizontal rows are called periods. Okay. Now across the period, elements change as they go across. Okay. They start off over here, what we consider the most metallic elements, and as they become over here, they become more non-metallic, even gases. Okay, and so things change across. It's called the periodic trend as it changes. Okay. Another trend as we go across, you see the number gets up here. This has to do with the number of protons they get. So as they go across, even though they take up less space, they have more mass. There's more particles in them, therefore they have a greater mass. Their protons and their neutrons are increasing, and that's another trend. So as you go across the table, you would expect them to be heavier. And since they're also taking up less space, they're going to be more dense, okay, as they kind of go across. But that's basically kind of that. Now, we didn't say, first of all, an element is just a substance made of one type of atom. So what makes these all different is that each one of their atoms are different, okay? And if you look at on the chart, it will give you the information that you need to know to do that. For example, the top number is the atomic number. Okay, we call it the atomic number. It's usually the top, could be on the bottom, but it's a whole number, okay? Because this number is equal to the number of protons that the atom has. And so this number is always going to be a positive number because you can't have half a proton. Now there's another number, which is on this particular one up here, but say for example hydrogen has 1, and then its number at the bottom is 1.0072 or something like that. Okay, and so someone says, well, why is that? What is that number? Well, that is the atomic mass. A long time ago it used to be called the atomic weight, but that's not accurate because it has nothing to do with weight. It has to do with the mass. And the mass is basically the neutrons plus the protons. Okay, because if you remember, neutrons have a mass of 1 AMU, protons have a mass of 1 AMU, but electrons are so small that their mass is 0. So basically, the atomic mass is just the neutrons plus the protons. Neutrons and protons are also known as nucleons because they are found, E-O-N-S, because they are found in the nucleus of the atom. So they're called nucleons. All right. Now, we'll talk at next lecture about isotopes, which basically has to do with the number of neutrons. But we will talk about that next time. All right. See you there.